Yeah, thank you for having me. Can you see my screen?
Yes.
All right, now I can't see any of you, so if you're making faces, I can't see you. Uh, Thanks for having me. I'm really honored to speak at CMU AI seminar. I've actually never been to CMU, so maybe post-pandemic era, I'll be able to visit Pittsburgh. I heard there are good bars and whatnot. But today I'm going to talk about interpretability, where we have been, where we are, and where we might be heading. And this is kind of talk that poses a lot of questions and some answers. And I hope that it would inspire some of you to think about these questions. I'm presenting work with a lot of awesome people inside and outside of Google who are listed here. And yes, ask questions, because otherwise, if I'm not in a good place to answer questions, I will postpone. But otherwise, please jump in. And remember, I can't see or read the chats, so just have to make some noise. So last couple of years has been amazing for the field of interpretability. There has been a lot of papers, workshops, symposium, and more importantly, folks started recognizing the importance of this area, which sounds obvious to us now, but it wasn't true when I first started working on this field. But I still think that we haven't walked very far. Interpretability is a complex problem. You not only have to worry about complex thing called machine learning model, but also have to worry about another complex thing called humans. And there isn't one mathematical definition of what interpretability is. And why? Well, the psychologist who's been trying to do that for centuries can give you a better answer, but simply put, humans simply can't be expressed using math. So one has to take more holistic and systematic approach to have an angle of attack in this problem. So it is a hard problem, but if it's not hard, it's not research. So in this talk, we're going to first visit our past, where we have been, by re-examining one of the most popular interpretability method with critical eye. Then I'm going to present a family of methods that are inspired by the past, by putting humans and users in the center in the design. Then I'm going to talk about where we might be heading, things we need to think about. So first, what we've been doing. We're going to focus our discussion today on a particular type of interpretability method called post-training interpretability method. What is it? Well, it's just that you have a model that somebody gave it to you, and you can't change that model. And you're trying to answer the following question. Given this model, find the evidence of prediction. In other words, if you have a model that takes a picture, predicts what's in the picture, answer why was this junco bird? Now, one of the most popular interpretability methods for these images, for images in particular, are a family of methods called saliency maps. Now, saliency maps, in a nutshell, uses a simple derivative of the logic with respect to each and every pixel to test, intuitively speaking, if I move this pixel by a little bit, how much would the probability of, say, junco bird changes? If it changes a lot, it's an important pixel. If it doesn't, it's not an important pixel. And thanks to this elegance behind methods and this idea, there has been an explosion of methods that does things like this. It includes some of my work from 18. So when you look at it, it kind of makes sense. Look at this bird. It highlights some boundary of the bird. Maybe the eyes were important. Some of my work or other work looks like it's looking at maybe the legs, maybe the cheek. Sure, it kind of makes sense. Now, we take a step back and kind of think about what these methods are trying to communicate to us. Now, remember, I told you that these pixels are the evidence of prediction. So whatever method we're making, it's a function of prediction. Now, if it's a function of prediction, when that input to that function, which is a prediction, if that changes, the output explanation should also change. And in an extreme case, if the prediction is random, so input is random, then the explanation should really change, because now we have a function, we give it a random input, output should really change. So we put that into test. What we did is we took a perfectly good trained neural network on images and got a bunch of saliency maps from a lot of images. And we copied that network and we randomized the learned weights from the top layer one by one in a cascading fashion all the way to the bottom layer. So remember, as soon as we randomize the top layer, the prediction is completely random. So input to this function is now random. So you would think that explanation should change, but it doesn't. Now, you might say, well, you know, these two saliency maps up and down, top and bottom, it's not exactly the same map. Like there's some sky darker here than that it's not here. But remember, the end goal, the end consumer of all these methods is humans. And as a human, I don't know if I will drive dramatically different conclusion looking at top or the bottom. The belly of the bird seems important. The chick part of the bird looks still important. So in fact, the methods, the pictures that I just showed you earlier, 3 of these are generated from random network, where predictions are completely random. Now there's A, B to F. I want you to guess. I will even tell you how many there are. So there are 3 of these are generated from random. So I want you to think about what the answer might be and maybe type it in the chat, maybe think about it in your head. Which ones are generated from random network? I'll give you a second. All right, so remember your answers. I will have a couple more questions later on. I'm curious if anyone can get all of them right. I'll be very impressed. So the answer is B, D, and F. These were generated from completely random network. And as you can see, I honestly can't tell the difference. I had to memorize what they are because I keep forgetting which ones and where I put what. So we did this for many, many images, for many popular saliency map methods, including my own work, and cascading randomization from the top layer all the way to the bottom layer. So the last column, you're looking at completely random network. And as you can see, some of these methods don't change their appearance at all. Now, shocked by this discovery, we decided to do something slightly different. So instead of randomizing a trained network, we trained a network with random labels. So what this does is you're training something, but the network doesn't learn anything. So we trained it with a random label with MNIST. It never learned the meaning of digit number 0. But as you can see, some of the methods looks like almost it might have learned what 0 is, which is clearly not true. So ever since this work came out in 2018, I've seen lots of reviewers requesting to run this method on new saliency map techniques in the review, and authors having to end up running it or they already included in the papers. And lots of great work, healthy, critical look at what we are doing. Lots of work followed. And I think this is exactly the line of work that we should be pursuing in order to do good science. And more recently, I just discovered these papers about taking even more fundamental, asking even more fundamental questions like, are the gradients really showing what we think it's showing? Some of the great papers, I highly recommend reading, skimming some of these papers. But after this work, we remained confused because we know that some of these methods, they show their experiments with domain experts like doctors, and they confirm that these methods actually help doctors to either faster or more accurate diagnosis. So are these methods still helpful for some end task for some reason that we don't know yet? And what are those tasks? So we tested with Turkers by intentionally introducing problems, common problems that machine learning engineers might encounter in their day-to-day life, like having wrong labels or having out of the distribution data, so that we can test whether any of these methods are helpful for some of these tasks. So what we did is we recruited Turkers, and we told them a scenario. We say, okay, you're working at a startup and you're selling animal classification machine learning model. And say your boss gave you this model and which comes with images, predictions of those images, and attribution maps, the saliency maps. And he or she asks you, okay, how should we deploy this model? Should we start selling this model? Then we ask them, how confident are you in recommending this model, and why? Was it because wrong or correct label or explanation, all in the Likert scale? And note that we gave the prediction labels to the users, and we debated this quite a while. Should we, because then folks might just look at the prediction label, for example, if there was spurious correlation, or actually more like the randomizing weights, then the prediction will show the randomness. So we debated quite a while. So it might confound our findings about if we just want to test the explanation. But we decided to go ahead and give the prediction label too, because otherwise it's very contrived scenario. It's not realistic. If you have a model and you're about to determine whether you're going to deploy or not, of course you're going to have a prediction too. So you will see some of those findings later on, but yet still we find many things that are interesting. So here's our second quiz. Here we trained a model with the spurious correlation. Now this is one model, and I'm showing you two pictures. There's ocean, obviously, and there's some bird flying over it. Do you think that bird was important for this classification? So the spurious correlation can be, bird could be spurious, or the background can be spurious, right? Meaning that the network might actually just be looking at the background, or maybe just looking at the bird. Which one do you think it is? Was it the bird or not a bird? I want you to think about it a little bit. And you can type your answers in the chat room, or just think about it. The answer is that bird was not important for the classification. We trained it with the background, and the bird is completely irrelevant for the classification. But even then, we see that a lot of birds are showing up in the attribution maps or the saliency maps. And here's the results from the Turker experiment. Again, we asked two questions. How confident are you in deploying this model for gradient method, for another method, and why? Subjects remain uncertain, which makes sense, which is good, because there was something wrong with the model. And also good that they were not confident because of the unexpected explanation. So they saw this picture and they're like, why isn't there's nothing, but why is, for example, this method looking at something in the middle? So this is good. This means it's helpful for this particular spurious correlation. These methods might be able to help humans to detect it. Now, some follow-up work that we're doing right now shows that some other spurious correlation, these methods are simply not equipped to express those spurious correlation, but for this particular test, it seems that it can be helpful. This is the last quiz. So another quiz here. Here we train 4 models, and some of these models are trained with this data set. This is Fashion MNIST, and some of these models are not, trained with something completely different. So this is the test time out of distribution data test. Now I want you to type in or think about what the answer might be. Which of these models thinks that this data is out of distribution? It could be 1, it could be 2, it could be 3. The answer is the 3 rows, bottom rows, are all out of distribution. The second row is only trained with MNIST. The third is type of bird and dog images. And this is just VGG ImageNet that was trained with the ImageNet. And when we asked Turkers, they were still uncertain. There's some confident answers, but mostly pretty uncertain. But not because of the explanation, but because of the wrong labels. Remember, we gave them the prediction label, and they can look at it and say, this is weird. I am showing a dress of some sort, but it's telling me it's a dog or a bird. But also interestingly, some folks thought that explanations were expected, as expected, the green bar here. So maybe those are the folks who rated this model to be a little more confident. So perhaps for this particular end task, these methods may not be very helpful. And we did this type of test for many other types of bugs. But let's think about, so those are things that we've been thinking of where the field has been on. You know, we had the sanity check test, which wasn't ran by anybody until 4 or 5 years later, after everyone or a lot of folks worked on developing saliency methods. So why did no one run it? And we didn't even set out to run it either. We were going to develop a new method, and we ran that test as a sanity check. We were like, oh, let's just check that we don't have a bug in our code. And it was the results were odd, and we thought, okay, we got to fix this bug. And that's where we went down to this path. So why was it? Why nobody thought about it? One of the reasons I hypothesize is that our confirmation bias acted strongly in here. So when we looked at the bird picture, we expected to see a bird in our explanation, and we saw a bird and we liked it. We saw what we expected to see. And that didn't help us to be critical about what we are seeing and wondering if we're really seeing what we think we're seeing. And from the second experiment, I believe that there won't be any one method that fits all the needs. There will be some methods that fits better in hinting spurious correlation, some other methods hinting better in auto distribution, and some other task will be better fit for some other method. So we need a set of tests for the users to learn which method is better for what they're trying to do, in what data domain, and for whom. And there's a lot more questions that we still have. Why could these methods be possibly helpful for these end tasks when it may not be a function of input? When we randomize the input, the function still shows something meaningful. So we remain wondering, and there are a lot of interesting questions that one can think about here. Any questions so far? Oh, actually, I should ask. So I'm curious. I'm now on a chat. I'm curious if anybody got one of them right. Has anybody got any one question right in those 3 quizzes? Anyone? Wait, nobody got. I don't
think, not from the chat channel. I don't think anyone got them all correct.
Oh no. Okay. If you did get all correct and you're just shy from telling us, do tell me. There will be a virtual sticker sent to you that says I got it all right.
I think there's a comment though in the chat.
Right. Neuroscience have been this for years. Animals to make face discrimination between monkeys and gorillas and learning background details. We're entirely wrong. Oh, interesting. Michael, if you want to, yeah, this is an interesting point. If you, yeah, let's discuss more about this later. This is super interesting. But for now, let's resume. Let's see, how do I write? All right, so let's move on to the present, where we, how we can do better. Methods that are inspired by the past, and each subsequent improvement, sort of new ideas whenever we stopped and trying to think how we can do better. So we talked about this axis of end tasks a lot so far. Some methods are useful, some tasks, and some are not. Now let's look at a different axis, which is another important axis, the end users, the humans who will be consuming these methods. Some might be machine learning experts, some might think about medical experts. And I argue that a lot of methods that we've been thinking about so far are for experts. The feature attribution, a lot of times feature attribution are for each and every data point, and that could easily overwhelm a non-machine learning person who just want to get a sense of how this model is reasoning about the problem. So this new work is inspired by thinking about for users who may not be machine learning person. So the problem we're thinking about is still the post-training explanation. Again, the model is given, and what we're trying to answer, for example, for this popularity classifier, we're trying to answer why was this a popular pizza? Now let's use that saliency map that we just talked about to help us think, what are we really trying to ask? So here's a saliency map for this picture. There's some pizza, there's some tomato is highlighted, maybe the wine is a bit highlighted too. If I'm an owner of a pizza restaurant, I wonder, okay, well, is it the toppings that I should really care about, that optimize for and spend more budget? Or perhaps it's the beverage. Maybe I should come up with a new cocktail list to sell more pizza. And is it true? Is this true for all pizzas that it's classifying, or is it just true for this particular pizza and this particular user's picture? The problem is that you can't express these concepts as pixels, especially across many images. And if the tomato or wine was part of the input feature, then you can attribute to that and you're done with it, but you didn't have those. I just came up with this concept of wine and pizza toppings after the fact. So the goal is to have, wouldn't it be great to have a quantitative measure of how important these concepts are after the training? And that's what this method does, TCAV, testing with concept activation vectors. It gets you a quantitative, a number between 0 and 1, how important the concepts that you came up with are for the prediction, even if that concept wasn't part of the training. So for instance, this method is able to translate how computers are thinking in pixels and tensors into what humans are used to think in things like concepts, pizza, cheese, wine. So I'll explain how this works. It's pretty simple. Using this example of you have, let's say, zebra classifier, and you're interested in how important the striped concept was. So first and most of all, okay, well, the concept sounds like a good idea, but how do you even define concepts and express that in neural network? We do the simplest possible thing. We learn a vector that represents the concept, and we call it CAV. And to do that, here are some ingredients. You have examples of concepts, some striped images, and you have some random images for the reasons that will be obvious soon. And you have this network that you want to investigate. And we assume that you have this function FFL that maps the input image to activation. Then what we do is we pipe in these images into a layer, and we train a linear classifier to separate concept activations from random activations. And we take the vector that is orthogonal to that decision boundary, and we call that CAV. So what is this vector? Well, it's just a vector that points from a random direction to the concept direction. And this is not a new idea. We've been doing this for a long time, like the word-to-vec, the man and woman vector. It's the same idea. And there has been a lot of evidence why this linear approximation in this complex space, at least locally, is actually means something semantically meaningful. So we do that. Now we have this vector. How do you use this then to get that quantitative number between 0 and 1, the TCAV score? It's also pretty simple. So remember we talked about saliency map with the derivative with logic with respect to each pixel. Now we're going to do something similar this time, but with this vector that you just learned. So we are going to take directional derivative of the probability of a zebra with respect to this vector, the striped vector that you just learned. And what this means intuitively is if I change the concept a little bit, by tiny bit, zero it a little bit, how much would the probability of zebra change? If it changes a lot, it's an important concept. If it doesn't, it's not an important concept. And we do this for many, many zebra pictures. And we just calculate the ratio of zebra pictures that gave you a positive directional derivative. So if you had 100 zebra pictures, 80 of them were positive with directional derivative, then your score is 0.8. This is just one example of defining TCAV score. I've seen others defining it in a slightly different way, use the absolute value of the directional derivative, and so on. So that's cool, but you talked about this vector CAV. How do we know that this is legit? Because we know in high dimensional space, funky things can happen, like adversarial examples. We are just completely over parameterizing this problem. So how do we know that this is actually a thing? So that's the next step, guarding against spurious CAV. So the whole question is, how can we quantitatively convince ourselves that we didn't have this CAV that gave you high sensitivity just by chance? There are lots of different ways to do it, but here's one way. Now remember, we learned this CAV using random images and trained a linear classifier. Now these are random, so you can plug in as many sets of random images as you want, each of which will give you a CAV. And for a target like zebra, you can get many TCAV scores for this different CAVs, all meaning stripes. And you can view these many TCAV scores as samples from a particular distribution. So if you have these stripes were important in zebra, you might have some nice Gaussian distribution around maybe 0.8, maybe 0.7. Then you compare this distribution with TCAV score for the same target, but with random concept. So instead of striped concept, you plug in another set of random images. And you run the t-testing to confirm that these two distributions are statistically significantly different. So all the results that we will only results that we'll show to the users is only when the CAV passes this test. And if they don't, when we say, sorry, you thought this concept might be important, but it turns out that network doesn't care. So we can't really explain using this concept you gave us. So with that, we have some cute results in the paper. First, sanity check experiment where we crafted a data set. We know the ground truth, and we show that TCAV can match those. And we have some other medical example. But I actually thought that I can show you real results that are done by actual doctors and scientists. This is work that came out of King's College London, who used TCAV for cardiac MRI classification. James et al., you were training a model that can be both generative and classification, and they're classifying the coronary artery disease, or CAD. And they used this biomarker concepts like EF and PER, given this image data set, and show that TCAV can confirm things that they were expecting, or they made some interesting discoveries using this interpretability methods. And because their model contained VAE, they can also generate images using this CAVs. For this particular case, they used the left ventricle concept in different timestamps and show that you can interpret using and generate different images using this concept. And when they plotted this concept vector using two principal components, it also shows up nicely. But the coolest part of this paper that made me really thrilled to see was that in the conclusion where they wrote, interpretability using known biomarkers allows the model's prediction to be placed in the context of a current medical knowledge and clinical decision-making guidelines. And this is exactly why TCAV is there, to translate from what machines think and machines' language to how humans reason about, how doctors reason about in this diagnosis. So I was thrilled to see this this part. Another really interesting work came out of DeepMind. In this work, they extended TCAV for RNNs. So time sequence series has different ways to define CAVs. So they explored a few different ways. First, they define CAVs that wherever the concept ends, so maybe this vector from the beginning to end, they explore defining CAV using start and end and sequence of CAV vectors as you go. And lastly, they explored ways just by subtracting the end and the start. And they came up with a few really interesting quantitative metrics that are useful for their electronic health record data set. For example, a presence of concept in one data point rather than many. What I also really like about this paper is that they had the sanity check. They generated synthetic data to make sure that the ideas that they had here, different ways of generating CAVs, make sense and which one worked the best. And after that, they also applied this to real data set, AKI, acute kidney injury, and where they showed that for this patient, when model prediction changed, this orange shaded region, the right concept that they expect to rise were also rising with a little bit variance at a time. And compared to very different distribution of this shaded red area, which is the random concept that they tested. And there has been a few other work on radiology and breast cancer to use or extended this work. My other favorite work is this work by Eric from Aerospace Corporation, where he used TCAV to interpret storm classification model. So the storms have different categories. I guess 4 is bad. I don't know if there is 5, actually. I have no idea. But they had this given satellite images. They were classifying which category of this storm is. And for concepts, he used, for example, here, storm I. And I actually met Eric at a conference, and he taught me that in his application, using the black background on his negative images, the random images, were really important because his concept images were all in the background. It's a satellite images, black and white picture. So having sort of similar distribution was important to make in this application work, which is like really important lesson. A few follow work, awesome work at Google too. Emily Denton's work on estimating the facial or what you call it, external features, how they contribute in the classifier. Ben Hutchinson also used this work for a language model to confirm that when the model was unbiased for LGBT comments, rightfully so, the LGBT neutral comments that is not toxic has decreased amount of its prediction in toxicity after unbiasing the model. So he used this as a way to confirm that the desired effect has happened after unbiasing the model. Any questions so far? Remember, I can't see the chat. Feel free to jump in anytime. So that's great. So we talked about some medical examples and other work, but what if you don't have the concepts? You know, you might have this awesome medical case where some concepts are given by doctors, but what if you don't know which ones you should be using? Can we automate this? So next is how we can automatically learn CAVs. This is work with Amirata, who is a PhD student at Stanford. The story is very similar, except this time you don't have examples of concepts, or maybe you don't even have random images, but you still have the network that you want to investigate. The idea is pretty simple. You take the testing training images or other held data or whatever of your choice. You segment the images using superpixel method. This is off-the-shelf, pretty well-studied method on semantically segmenting images with different granularity. Then we collect these, what we call image patches, pipe them into the network, do a smart clustering with outlier remover and all that, and score each of these clusters, consider them as a concept, and then evaluate the importance of their concepts. Now, it's a simple method, and one of the most important things is validating whether these discovered concepts are actually meaningful or not. So we went through a few human subject studies. First was intruder tests, which when we give users like say 6 pictures and 5 of them are discovered concepts, one of them is an odd one. We randomly inserted one and we ask people which one is the weird one. And we compare that, the performance of humans, to hand labeled data set, where these are not discovered ones, but still have a odd one out. And we show that the performance of subjects are very similar in either cases. Now, the next human experiment, we asked humans to name these concepts. Well, we first asked which one is more meaningful, and then we asked, okay, well, for the meaningful one, for example, this one, what would you call this cluster or the concept? And this was kind of surprising to me that 56% of the Turkers said the same thing. It was human, or some other cases it was hands. And if you count the top 2 things that they listed, then 77% of people actually said exact same words, which is quite surprising and shows that these discovered concepts for this data set were consistent enough that people would put the same word to name that concept. We did a few other quantitative confirmations by adding the top 1 to top 10, top 15 patches. We showed that, yes, prediction score goes up and it's better than random, and worse than if we reverse the order of the patches, the least important patches first. And we do the same thing by deleting it too. Some of the results that are some surprising and some not surprising. For example, dumbbells. It's pretty well known that the dumbbell class in some of the models don't look at dumbbells at all. They only look at the people who are holding the dumbbells. And of course, unfortunately, most of these folks, majority of them have light color skin. It's something that you may not want. And we're also happily surprised that images like this busy also can find this very complex patch in this image, and that carves out the humans. It's like one human, and this is, I think, different human's arm or something, and it was able to find that as the most salient concept. So that's cool. But how do you know when to stop? You can add tons of more images and just keep going. How do you know when you have enough? So that's the work that we did with Chiquan, actually from CMU. This picture has background in San Francisco, but he's in CMU. So this work is about discovering complete set of concepts. In the basic idea is that we're going to decompose the feature layers, activation or whatever you call it, into concept vectors, and we're going to try to reconstruct that back and trying to minimize that error while optimizing for also optimizing for a few other objectives. And we come up with a Shapley value for each concept and define what that is. For the definition of completeness, we use this particular one. It looks complex, but it basically follows a sort of PCA definition. So if you under some minor assumptions, this metric is actually equivalent for top K PCA vectors, which is nice because it comes with nice theories and guarantees of PCA. And here's some results. This blue line is the ACE, the automatic discovering method we just talked about. And it's comforting to see that as you add more concept, the completeness score goes up in ACE, which is good because that's what we expected. But of course, not as good as this particular method that optimizes for that completeness. And this particular method learns concepts not just for each class. ACE was learning it for each class. This learns concepts for all classes at the same time. Because you can imagine like zebra and lion might have some overlapping concepts of like jungle or something. So that's cool. You can discover concepts and somehow that they're complete. But if you already have these labels of the concepts that are relevant, why can't you just build a model from scratch? So that's what we did in this work of concept bottleneck models. This is work with awesome students at Stanford. What we did is we have the concept labels and we train a network that had this bottleneck where each neuron is aligned with the concept. And you only need labels for concepts at the training time. You don't need it at the test time, of course. First thing that we need to check is that these, by introducing this structure in the model, we're not sacrificing giving up any performance. Now, there's a lot of talk about the inherent trade-off between the performance and interpretability. A lot of cases, my work and other folks' work, that trade-off doesn't really exist. Often, when you carefully think about how to build a structure that aligns with your data that you're interested in, we often actually gain performance rather than losing it. And here is yet another example of that. 3 different ways to train the same model. We show that our performance is pretty good, in fact, a little better than without this structure. And this kind of makes sense because regularizer is a type of, you can think about that as a type of structure, which almost always improves our generalization than hurting it. Another good thing about building this model from scratch is that now you can interact and control the model. So if you don't think that trees or lions should matter in this predicting the zebra, you can just cross them out for prop and get the prediction. And this becomes particularly useful when you're working with domain experts like doctors who may look at this model and say, well, that symptom is just completely not relevant for the diagnosis. It shouldn't matter. Then we can intervene. And we did exactly that with this arthritis data set where we pretend the concept labels. We held out a set of data points where concept labels are given by doctors. And we show that as we intervene more concepts, we can achieve lower error, which is exactly what we expect. Check the time. So what about, so this is all great. You build a model from scratch, but whenever we think about interpretability, we get questions about causality. Why can we make this causal? Well, my quick take is that, whenever you can make it properly causal, you should. But often my experience with working with causal inference is that you definitely need to do more work. You either have to come up with a causal graph or think really, really carefully about confounding effects, your assumptions. And with that, if that work, so for example, building generative model, which is what we're about to do, works out for your domain, that's great. That's perhaps what you should be doing. But it's not free. Is the takeaway. So let's talk about that causal TCAV work. This is work with Yash, Amir, and Uri. The basic idea is pretty simple. We wanted to calculate the ATE. Here we call it causal concept effect. It has a slight subtle difference from ATE, so we decided to name it slightly different. And the idea is that there are some concepts that playing a role. Some of them might be have some interaction that together generates an image, and that generates the classifier output. And to calculate the ATE, what it is you have some concept, you're calculating the difference of the prediction when that concept is on versus when that concept is off. So for example, if you have a gender classifier, you want to test whether glasses made a difference. You have a picture with that person with glasses and without glasses, say same person, and you calculate the difference. Now, of course, you don't have this picture, the same person without glasses, because you only have observed data and you're not doing active controlling. So that means that we need to build a generative model. Now, there are many different ways to build this, and we tried many, and these are 2 things that worked out. You can build a model that and decoder and encoder and just use the decoder and sample the Z latent distribution and to generate a bunch of general distributions, many distributions to calculate the ATE. Or you can test a specific set of data points by having inputting that image, that data point in encoder, get the Z and do the decoder to calculate the when concept is on. And we tested this using a data set that has ground truth because we made up this data set. this data set has scenes like bathroom and shower, and we copied and pasted the dogs or backpacks in random locations in this image so that we can completely control the distribution of where dog appears, for example, and how often with what classes. So we know exactly how it influences the classifier. And when we compare it to ground truth, we show that this particular method actually works really well with by matching the ground truth. Slightly less good for encoder and decoder. So check the time. So in summary, we talked about this method that puts users, particularly non-machine learning expert users, in the center of our design process to create explanations that are quantitative and using concepts that users come up with after the training. We talked about how we can do it automatically and in a complete way, or train a model from scratch, or making it causal. Plenty of limitations that I would love to discuss and think about. You can't really express the concepts unless the concepts are sort of visual in your data, not just visual, but present in the data. Like if it's love is one example. It's high level. It's hard to think about how you might even be able to show an example of that. And discover concepts that the method we talked about, it doesn't have names. So for images, it's easier because you just have to scan a bunch of image patches and say, oh, it's human. But it's much more difficult for different types of data set, language or graphs. And another thing is that humans might think that a concept means something, and that almost always has a gap between how machines understand a concept. So an example of this paper, Carrie Kai's work, actually thought about this carefully, and by showing a slider of more and less concept and sort pathology images with respect to that concept to give help humans build a mental model of what that concept might look like. What did machine actually learn about this concept? Is it aligned with my idea of this concept or not? I was really thrilled to see the response from outside of academia, because again, the whole goal of this method was to help anybody use machine learning, because the machine now talks in your language as opposed to you having to learn their language. Sundar talked about this work, and not only that, he explained how it works in his keynote, which was awesome. It won the UNESCO NetEx Pro Award selected as one of the 10 cutting-edge digital innovations with potential of profound and lasting impact. So with that, let's talk about some future, where we're heading. A lot of work to do. We talked about this axis of n tasks, lots of interesting and important tasks that we might be using these methods for. We talked about user axis, of who we are trying to explain and whether that would make sense for them or not, or helpful. And there will be a lot more other axes that we probably haven't thought about yet, or that are specific to a particular domain. So there's a lot more, by multiplying these things, it will create a lot more cases, which will bring more interesting questions and not many answers. As we explore these, I think there are three things we really need to keep in mind. One, proper evaluations. We really ought to design a sanity check or a data set, a synthetic data set, where you know the ground truth, so that you can at least confirm in that kind of contrived setting your method works. And you're trying to just keep doubt that your method might not be doing what you think it's doing. And evaluate with humans. Remember, none of these methods would exist if humans don't exist. So we really have to check with our final consumer to see if it actually works or not. Also, let's remember that humans are biased and irrational, that the confirmation bias or other sorts of biases that we have, it's not going to go anywhere. We have to live with it. And it's not to say that, oh, we have to just really try hard not to be biased. No, I actually think that we can do better than that. We can design that bias in mind so that we say carefully craft the human subject experiment to tease out that differences. For example, you can provide a control condition and give a random explanation or explanation with random prediction. And doing that controlled environment, controlled settings will really tease out what this explanation is contributing to. And let's keep it critical about what we are doing, and so that we can, it helps us to see what we are doing with really skeptical minds. And we really have to build onto our past selves and learn from mistakes that we've made in the past to move forward and do good science. With that, I'm happy to answer any questions you may have.
All right. Thank you, Bean. All right. Does anyone have any question? Yeah, and clap. Thanks, Layla. Okay, maybe I'll start with a question, I guess. So I think one thing that was not like fully discussed was I think adversarial examples, right? So let's say if you generate the calves from adversarially perturbed images, do you still think these calves will be the best calves that will make most sense to these interpretability models?
Oh yeah, I'm glad you asked that question. We actually tried it in our original paper. Very limited results, but probably a beginning of an answer. So what we did is we generated an image, white noise image. We generated two types of adversarial images. One white noise, but definitely predicted as zebra, and an actual image, but flip a couple pixels to make it predict as a zebra. And then we find the distribution of concepts. So we tested striped, the zigzag, and some other patterns. And what we saw was that the distribution of these each different adversarial set of images were very different from non-perturbed images, which was very encouraging. We didn't do any further experiment on that, but I had a lot of discussions with folks, for example, meta-learning folks who thought that by looking at sort of one step up and more abstract level like concepts, you might actually able to capture that small variance a little better. So that applies to meta-learning, maybe general concept also works better, but also applies to adversarial case where, just small things change and that propagates much bigger in the concept space, and therefore you can catch it better. Now, do I think it's the answer for adversarial example? Not at all. No, I mean, no matter what, you can totally fool any concept-based method or concept-based model or whatnot. It will be able to fool anything all the time.
That makes sense. Yeah. Any question from the audience?
Hi, I'm Alex. I'm a PhD student at the Human-Computer Interaction Institute, so more on the interactive interfaces side. I've been thinking about TCAV a bit more just for like treating it as a classifier, like you could bootstrap it as a quick classifier for different concepts. But then I always get to this point where I'm like, the original model was maybe trained on ImageNet, so will it be able to distinguish kind of these more nuanced, fine-grained human concepts? Like, for example, if not only I want to find people wearing glasses in my data set, but I want the concept for clear glasses in my data set, how do I know that this feature space that my model has learned is expressive enough to be able to distinguish that? Or is there a way of like teaching it that without having to just label a ton of data?
Yeah, great question. There are a couple of answers to that. One is that we can craft better the concept examples and particularly the negative data set to better contrast that. So you want to have, let's say you have glasses concept and you have clean glasses concept. And let's say you don't have a dirty glasses concept. Then you can just learn a vector where clean glasses concept is positive and the rest of glasses are negative, or the random images. And that we call relative CAVs. And in like Carrie Kai's, the pathology example that I briefly showed, in that case, that worked out so much better than the global CAVs. So what she did there was we're looking at what do you call it, biopsy of cancer patients, and we looked at 10% cancer, 30% cancer, 50% cancer, and we learned the relative CAVs for translating between those different categories, which was helpful. So that's one. But the second thing is, I think, perhaps closer to what you're working on, I really think that designing a better interaction with human experts, and that might involve, interface, or maybe it involve some smart interaction design and HCI expertise, is going to be just crucial for bridging that gap. Even if you have clean glasses and you learn a vector and those kind of reasonable things, there might be some gaps, there might be some confoundings in their correlations. And to discover that, we really have to invest a lot more in the designing better interactions.
Super cool, thank you.
There is also a question in the chat by Sharia. Sorry if I pronounced that incorrectly. Yeah, so the question is basically, how would you go about addressing the problem where most concepts will be missing?
How would you go about addressing this problem? Most of the concepts are missing. You mean that missing the label, or it's non-existent in the data? I'm assuming the former, right? If not, let me know. So if you meant the former, meaning that you don't have the labels in the test phase of the new data. So you have concepts in the training, but the concept just didn't exist in the testing phase? Is that what you mean? I see. So in that case, if there's a concept that was important enough that model learned, and therefore like it passed the statistical testing, but at testing that concept somehow disappeared, then I would expect the score to be basically like random. So when we compare with the randomness, the mean, if you plot the mean of that random versus random TCAV score, then it would like right along that, and 0.5 most likely at the testing phase. But I think you have a different problem if this happens a lot, though. Like if you have a concept that was really important and passed all the testing, but in the test data somehow that concept disappears, then you might have auto distribution problem, or maybe some other problems to worry about, and not just interpreting the network. Or maybe you can use this as an interpreting whether your distribution has changed. If they all come out 0.5, I guess you can worry about that.
Cool. There's a new question in the chat.
About concept complex score, my understanding is that will be some part of the new work decision in terms of humors and concepts given this 0.9 or 1 concept complex score means. So you mean that like concepts, when concepts aren't really human understandable concepts? Is that what you mean? Okay, yeah. Oh, it is a great question. So I've been thinking a lot more about this. So what happens if and in a way, like the transition from discovering concept, the ACE work, to completeness concept is kind of aiming at how much of concepts can we actually extract. So for example, I am working with superhuman networks, like I'm working on AlphaZero and interpreting AlphaZero with DeepMind folks, and I am almost certain, although I don't play chess, almost certain that there will be concepts that humans simply can't understand. Then my hope is that the completeness score will will be lower, like 0.7, and we know as a human, okay, 30% of this we may not be simply able to understand. And how do you and that's the dream. That's the dream. Whether we and that will happen if the ACE cannot actually do the clustering and visually do the clustering for the image case. So 30%, then you would identify, okay, 30% I just can't identify. Now, if it's also possible that ACE will cluster something and we think it means something and it actually doesn't mean what we think it means. And I think that's when I go back to the work of sanity check and testing to really try to nullify that hypothesis that we are seeing what we think we're seeing, or we are not seeing that what we think we're seeing. So all these work, this talk has more questions than answers. I think everything that we do, we have to be really skeptical about what we're seeing and confirm that we're not just seeing things because we like to see that.
All right, thank you for the question. Any other question from the audience or follow-up question or comments or feedbacks? Okay, well, yeah, if there's no more question, then I think we're a little bit over the time, but let's thank Bin for this amazing talk. I wish we could like clap actually. Yeah, and usually we would actually invite the guests to visit CMU. So hopefully one day you can actually visit CMU physically to give the talk.
I'd love to do that. Yes.
Yeah. Hopefully, soon after the pandemic, in the post-COVID era.
I think it's coming. Thanks for coming.
Yeah. Okay. As a reminder, we're meeting again at the same time next week, and we'll have Elon Rosenfeld from MLD talking about some of the recent work that he's doing. So thank you, everyone. Thank you, Bin, especially for attending the seminar today. Take care.
Thanks for having me. Bye.